to present I'm a naturalist, not a meteorologist. I have trouble with that word. Okay, part one, weather, climate, and the rhythms of nature. Randy's bio, however, reveals that he indeed has a lot of meteorological experience working across military, private sector, and federal government. He is a retired weather officer and has supported global operations, the intelligence community, and satellite programs before advancing weather innovation at the Federal Aviation Administration. He is currently the founder of Bass Weather Services, providing forecasting, research, and consultation to businesses and legal teams. And so at this point, I am going to turn this over to Randy. There you go.
All righty.
And you can go ahead.
Great. Well, thank you very much, and welcome everyone, and thank you for attending. Um, as Patty said, I really want this to be somewhat of a um, and want you involved in it as well. So if you do have any questions, please let me know. Sometimes during as you're giving a presentation, the way Zoom is set up, sometimes it's hard to see the chat. I do have it. Well, I'm trying to open it. Um, but sometimes it's difficult to see things. So if you do put a question in the chat, and I don't answer it immediately or don't see it, just butt in and let me know that it's there. But please, if I'm going to have some questions here, so please, feel free to speak up if you can, or put things in the chat, and we'll go along with that. As Patty said, my name is Randy Bass. I am the owner and president of Bass Weather Services, and I actually started my company. And let's see if this works. There we go. So I'll do a little bit more about myself, and then we'll get into the really meat of the thing, the course. We're going to talk about the relationship between climate, weather, and phenology. Talk about factors in weather that are in nature that affect climate and weather. Then we'll do some basic principles of weather observing. Then we'll go into weather safety, some common weather alerts, weather forecasts, and then I got a video at the end. I think not only will you enjoy, but you'll probably recognize from an event that I'm sure if you're not aware of, you probably lived through it. So we'll show you that. So of course, this is part one. This one, I'm really just going to be focusing on weather. When we do the one in March, I'll be focusing on climate, but we'll talk a little bit about the difference. So again, my biography, I have a bachelor's and master's degree in meteorology, a little over 36 years, actually going on 37 years of experience now. As Patty said, I'm a retired Air Force weather officer. And about a year ago, a little over a year ago, I retired from the FAA after being there for 12 and a half years, finishing up the last 2 years managing the aviation weather division, where basically we oversaw the research in aviation weather, things like turbulence, anything that affects flights. And I'm sure you've all been affected somehow by weather on a flight. Whether it was turbulence or the wind slowing you down, or thunderstorms or something like that. So we were working to mitigate those impacts. I'm certified by the American Meteorological Society as a consulting meteorologist. There's only about 200 of us in the country right now that are actually practicing. I was named a fellow by AMS, which is 0.5% of all meteorologists. So I was very honored to receive that last year. And obviously, I own a weather and consulting and services business. doing a lot of expert witness testimony where weather is a factor in the legal case, and then doing some weather forecasts for industry and consulting for business. And then I do a little bit of teaching like this. So we're going to start out with a pop quiz, and like I said, if you are able to speak out, please do. Or if you can put something in the chat, that should be okay. Um, Although I'm still having trouble seeing that, but anyway, we'll go ahead and start out. And with this first question, true or false? Weather forecasts are wrong more than 50% of the time. And if anybody want to guess? And I see a false and a true, um, and a true, and I'm already sad because I've seen trues. There we go, false. So false. So the reality is weather forecasts are probably right 80 to 90% of the time. But those times we're wrong, boy, do we hear about it, and those are the ones you remember. When we tell you that it's going to be 72 degrees and sunny, and it is, nobody remembers that. But if we say it's 72 degrees and sunny and you get a thunderstorm and it ruins an afternoon outing, you don't forget about that. So that's why people think we're wrong actually a lot more than we are. Um, and now we do a pretty good job out to about 3 to 4, even 5 days out. So next question. What weather phenomenon kills the most people in the U.S. on average? Tornadoes, floods, lightning, or none of the above? You see heat, floods, none of the above, heat, and it's technically it is floods. However, that is only because, and you're right, so it's technically B or D. The true weather phenomena, as far as tornadoes, floods, lightning, things like that, it is definitely floods. Kills many more people. However, heat technically does kill more people each year, but it is not usually that is not a direct cause. Um, that is heat you know kills people, but it triggers something else that causes the death, not directly related to the heat. So it's very hard to sometimes directly attribute those deaths to the heat. But yes, that's a good point that many times it is the heat itself. Uh, third question number 3, true or false? The terms derechos, polar vortex, haboob, bombogenesis were all coined in the last 20 years to explain weather conditions that had never occurred until the 21st century. So anybody have a guess on that? False, true, false, false. Okay. The answer is false. These terms have actually been around, most of them around about 100 years or more. They just came into vogue in the last 20 years because as as social media and things and weather itself just became more of a hot news topic. Um, those terms caught on with the public. But yeah, they've been around for years and years. Nothing new there. Oops, hit it twice, so we'll do twice. True or false, a car will protect you from lightning strikes. Let's do that one first. True, true, true. False. So generally true. A car actually will. It's basically a Faraday cage that the lightning would hit. If a lightning does hit a car, the metal around it, surrounds you. The the electricity flows through that. Now, if you have your windows down and your hand out, or you have a convertible, then it does not apply. So um, there are exceptions to that. True or false? It can only snow when the temperature is below 32 degrees. Yep, I can already see the answers coming on that. That is false. Obviously, the temperature can be sometimes as high as 40, 42 degrees, and it can still snow. It all depends on what the temperatures are above the surface, and we'll even talk a little bit about that coming up. All right, climatologically speaking, it's almost like meteorologists. What is the date within 5 days or so, the coldest day of the year in Maryland, and what is the warmest day? And oops, and I'm looking for a particular date for that. Anybody has a guess? So we all so we all know that winter actually starts around the 21st or 22nd of December typically. And I see a couple of 31st of January, the February 2nd, and that's actually pretty close. Technically, it's around the 21st of January, and then the warmest day is right around the between around the 15th and 20th of July. So there's actually a lag in the coldest day of the year and the warmest day of the year versus the actual uh, uh, beginning of summer and the beginning of winter. So, true or false? Winds in a tornado always spin counterclockwise in the northern hemisphere. I see a true, true, and the actual answer technically is false. Um, but about 99 and probably 99.5% actually are do spin counterclockwise. But you do occasionally get the random tornado that does spin clockwise. Uh, they can be almost as strong. Typically, they're a little bit weaker, but occasionally you will get one that spins in the other direction. We still don't know why. There's still some research going on in that. All right, what is the most common greenhouse gas in the atmosphere? I see water vapor, CO2, CO2. Okay. And I saw methane. All good gases, but or all good guesses and good gases. Um, but technically, it is water vapor. Water vapor is a greenhouse gas, and it is much more common than any other greenhouse gas, probably by several magnitudes more. Um, it just isn't typically recognized as one, but it is a greenhouse gas. All right. One more, or next to last question. What's the main reason why tropical storms and hurricanes rarely form in the Atlantic Ocean and Gulf of Mexico in the winter? And I see water temperature, colder water, wind patterns, water temperature and heat, and really it is actually water temperature. That's what keeps it to from forming. You really need water temperatures around 82 degrees before anything really occurs. So um, back by the time you get into winter, the the water temperatures drop back down in at least in the 70s down in those areas. So you uh, rarely get a tropical storm. And then finally, last question. True or false? If you see Jim Cantori in your town, you should immediately evacuate. And this is for folks who watch the Weather Channel. True, 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 true. Yep. Um, and yeah, you probably should. If he's in your town, something bad is going on. Um, so you know, I know it's funny. I like going to the Outer Banks, and I've talked with some folks there. They absolutely can't stand him because when he comes to the Outer Banks, the tourists all go home, and it really cuts into their economic uh, intake. So they do not care much for Jim there, but. Uh, I've met Jim a couple of times, and he's not a bad guy. So all right, let's move on. So we're going to now get into the meat of this. Um, so meteorology is actually from the Greek meteoros, meaning lofty or in the sky, and logia, meaning to speak or to explain. So basically, meteorology is just to speak or explain about things in the sky. We do not study meteors, obviously, even though I've been asked that, and have even received a couple of emails asking if I can identify a rock that someone thought was a meteor. And I could not because that's not my job, but I pushed them off to the right people. So um, one more question. Does anybody know who is considered the father of meteorology? No, it has not Ben Franklin. I guess you could say he might have had the key to meteorology, but he was not the father. In fact, the father of meteorology is Aristotle, going all the way back to uh, Greek times. So the difference between climate and phenology, weather is the observed atmospheric conditions at a point in time. That's what we're getting right now. Climate is really the average of the recorded atmospheric conditions over time. So it's what you basically expect you would see at a certain time of year. Like I said, you know, excuse me, typically the hottest day of the year is around the 15th of July, meteorologically speaking. Rarely is that the actual hottest day of the year. That's weather. Climate is what you would expect. Phenology, which we're not going to talk about, is the study of plant life and animal life cycle events that are affected by weather and climate. You all probably study that more than I do. So, so again, what's the primary influence on all weather and climate? And again, a question for everyone. And there's a pretty good hint right there in the picture. I see water. I see the sun, and you're absolutely correct. It is the sun. Without the sun, we'd have no weather, and then of course we'd have no life. So the sun really is the main influence. The second largest influence on weather and climate is water, of course, and the oceans and the circulation of the oceans. So, as the slide shows, you can see these ocean currents. We have the Gulf Stream right off the coast that pushes into the North Atlantic current, and that's why places like England and uh, Wales, Scotland, those areas, even though they are just as far north as portions of northern Canada, have a much warmer climate than those corresponding areas because that uh, North Atlantic ocean current uh, pushes a lot of warm water up that way and keeps them a lot warmer than you can see even the Alaska current and in that range. So oceans really do play a big factor in overall weather. And finally, the third largest influences on weather and climate are the Earth's rotation, the tilt, and the revolution around the sun. So that's why we get the seasons as the due to the rotation. You get the uh, and then the tilt of the Earth, so that you get sun on different parts throughout the year. And then, of course, you get the day-night temperature changes because of the rotation. Um, but the net effect is the Earth is unevenly heated, which creates temperature differences. Those temperature differences create pressure differences, and pressure differences actually cause wind. So that's really where the wind comes from. And just a neat picture of the uh, as we go from day to night and then back on the in the loop. So, all right, we're going to talk about weather observations now, and typically, wanted to start at this foundation because weather observations basically key everything else that we do. So, a typical weather observation consists of measurements of temperature, humidity, or the amount of water in the air pressure, wind speed and direction, visibility, cloud cover, and of course, precipitation. We have some that do a little bit more than that, but those are the basic ones that almost all weather systems record. So temperature is, is a physical quantity, expresses hot or cold, measured with a thermometer. Uh, we have three scales. We have the Celsius scale, the Fahrenheit scale that we're all familiar with, and then there's also the Kelvin scale. And I've shown you three examples here. Water freezes at 273.15 degrees Kelvin, and it freezes at 0 degrees Celsius and 32 degrees Fahrenheit. Um, and then you can see that, water boils basically at, we know at 212 degrees Fahrenheit and 100 degrees Celsius. Celsius and Kelvin are basically the same scale, just um, moved over a little for Celsius. Uh, and then you can see the Celsius to Fahrenheit conversion there, which I'm not going to go through. And the same as you going from Fahrenheit to Celsius. Basically, it's for every 9 degrees Fahrenheit, you get 5 degrees Celsius. And then you have to add the 32 degrees for the temperature. So that's kind of, the easy conversions to remember. 10 degrees C is 50 degrees Fahrenheit. 30 C is 86. Minus 10 C is 14. And then the good one, minus 40 C is minus 40 Fahrenheit. It's the only time they really match. And these slides will be available after this. So to everybody, I'll see about getting them over to Patty, and she can make them available to you so you can have this chart if you want to. Humidity is the amount of water vapor in the air, and the amount of moisture in the atmosphere. Now, there's several ways to express that. Absolute humidity is the water content of the air expressed in grams per cubic meter or grams per kilogram. Usually the only people that care about that are meteorologists and scientists. Most folks are very familiar with relative humidity, and that's basically a percent that measures the absolute humidity relative to the maximum temperature that would hold that much water. So if if your temperature is 68 and your dew point is 68, then your relative humidity is 100%. And then it just scales down from there. Specific humidity is a ratio of the mass of water vapor to the total mass of the moist air parcel. Again, nobody really cares about that except scientists. And then the other one you may hear about is dew point, and that's the temperature to which that air parcel has to be cooled down to so that you get that 100% relative humidity. So if you see a temperature of 50 degrees and a dew point of 32, it just means that to get down to 100% humidity, that air part would have to be cooled down to 32 degrees. And let's see. So, right. So atmospheric pressure is the force exerted on the Earth's surface by the weight of the air above it. And the air actually does have weight to it. We just don't feel it because we're used to it. It's typically measured by a barometer. The actual pressure is the atmospheric pressure at the level of the barometer. Um, and there are some corrections due to temperature and gravity, instrument errors, and things like that. But a typical barometer reads the actual pressure at that particular point. The station pressure takes that uh, pressure at that location and then manipulates it based on the level of the elevation of that station above sea level. So station pressure is the base value from which sea level pressure and altimeter settings are determined. Um, so that is usually what we use in uh, we take that and then uh, take that down to a sea level pressure, which is the atmospheric pressure at a mean sea level. But by doing that and using the station pressure, it standardizes the pressure across the board so that you're not dealing with elevation. Um, and so therefore we can use it for aviation and other applications. So it's really important to it basically gives you a standard reading for everyone. Um, the question is, how is atmospheric pressure impacted by wind? Um, and that's a good question. And if I'm not mistaken, here it is. So you must have seen my slides. So the wind is the air in motion relative to the surface of the earth and is generated by the pressure difference. So as the as you get a low pressure area that forms, like the one that came through the other day, and we got some freezing rain and sleet here. I'm not sure. I can't remember. You probably got a little bit of it in your area as well. That low pressure area that then became the nor'easter that moved off the coast. Um, the Earth really wants to be in balance, so there's the corresponding high pressure that was over the Great Lakes then. The difference in those creates that wind, and wind is nothing but air trying to go from high pressure to low pressure to even out things again. So it really is generated by the pressure difference to try to get things back uh, into a static mode. Um, it is affected by the Coriolis force, which is the spin of the Earth's rotation, and of course friction from the being near the ground. Um, Wind does occur at different levels throughout the column of atmosphere, and you'll I've got some examples of that. And it's measured by an anemometer or wind vane, but there are other ways to do it. Radar, LIDAR, which is basically uh, using another type of radar. Microwave and other techniques can be used to derive wind speed and direction. You typically hear about the jet stream, and that just refers to the maximum winds, usually in the mid-latitude westerlies and concentrated in the high troposphere, typically around somewhere between 25 and 40,000 feet. Um, can be anywhere in that area. It's usually indicated where it is reliably determined that the wind speed is equal or exceeds 50 knots. And I but and I had a couple of charts on that, but I took those out just for the sake of time. But they are in this package when you get it. Um, but the combination of temperature and wind creates a wind chill, and that's a measure of how cold people feel due to those combined effects. It's based on the rate of heat loss from exposed skin, and both, obviously temperature and wind removes heat from the body. So as the wind speed increases during cold conditions, a body loses heat even faster. So eventually the internal body temperature also falls, and that's where you get hypothermia. Animals also feel this, so it's not just humans. That's why you need to bring your pets in at night when the wind chill gets really low. But inanimate objects such as vehicles and buildings, they don't feel wind chill because they're not living organisms. And you see this chart here that typically if the temperature is above freezing, um, it takes a lot of wind to really drop the wind chill down a lot. But once you get below freezing, and especially when you get into the teens and single digits, just a little bit of wind can create a lot colder feeling conditions. So that's why we push wind chill when we hear about it and know that it's going to happen. Uh, Similarly, there's a heat index, and that's an approximation of how hot it feels. But instead of temperature and wind, it's temperature and relative humidity. So it's the amount of moisture in the air. So the more moisture and the hotter it is, the higher the heat index is. And of course, we see this a lot in the summer. And you'll hear things like the heat index is going to be 105 today. What they normally don't tell you is that is in the shade. So you really need to add about 15 more degrees to the heat index value when you're out in direct sunlight, whether you're working or hiking or playing golf or something where you're in sunlight. You need to add about another 15 degrees. A heat index of 105, you're actually seeing a heat index around 120 if you're out in the sun. So um, it's obviously very dangerous and does contribute to a lot of life-threatening conditions. Clouds are the next thing we're going to talk about. Clouds are typically made of water, either liquid or snow, but there are a couple of or liquid or solid, but there are a couple of exceptions we're going to talk about. Clouds typically form when air rises. As that air rises, the air temperature cools, and then it reaches its dew point that we talked about a little while ago. Reaches temperature, and then it becomes saturated, and the little water molecules adhere to some kind of nuclei, a piece of dust or something that's in the air, wraps around that, and these tiny little water droplets form. And then as they continue to form, and you get more and more of them, and basically into the millions, that cloud begins to take shape. Fog is nothing but a cloud only close to the Earth's surface. So if you hear somebody talking about fog, just remember it's nothing but a cloud. It's just a lot lower than a typical cloud. Um, um, but really, any collection of matter in the atmosphere that's dense enough to be seen by the naked eye may be referred to as a cloud. So you hear about dust clouds and dust storms, or a smoke cloud. Those are considered clouds. They're the two exceptions to the water cloud, um, and they typically don't last as long, but they uh, but they are still clouds. There are 10 different types of clouds you've seen here, and we'll go through several of these here in the next few slides. But cirrus and cirrocumulus, the cirrostratus, if you see the word cirro or cirrus, that means high. Altocumulus, altostratus, nimbostratus, um, those are typically mid-level clouds, and alto, um, actually, we'll talk about the um, a little bit about those and why they're called alto when alto does not mean mid. And then the rest of them are typically uh, lower clouds, or at least lower base clouds, but things like cumulonimbus clouds can obviously extend very high up into the atmosphere. Like I said, most uh, cloud names contain Latin prefixes, so when they're combined, give you an indication of the cloud's character. So alto means mid-level, although alto, as I was about to say in the last slide, is actually Latin for high. But in this configuration, alto is mid-level. Cirro and cirrus is it means feathery and wispy. Cumulonimbus or cumulus and cumulo means heaped up and puffy. Nimbus is rain bearing, and stratus is a flat layered and typically smooth cloud. And so here's the clouds by height in this one nifty picture, and you can see things like the cumulus cloud on the left, the big cumulonimbus cloud as the thunderstorm, and then nimbostratus is more of a kind of a wintertime occurrence when you get those low-level clouds, but yet they're still precipitating. Um, Stratocumulus, altus, semi or altocumulus, cirrus, cirrocumulus. You've seen all of these, um, and of course stratus. Um, what we consider high clouds typically are above 20,000 feet. They are almost always composed of ice crystals because it's well below freezing at the altitudes. Typically, they can be thin and white, but sometimes they can actually appear to be different colors due to the angle of the sun. Especially, they may look a little bit yellowish or red. Um, and I've even seen some bluish and green out of them if the ice is caught just right. And again, these examples: cirrus, cirrostratus, cirrocumulus. Mid-level clouds are between about 6,500 and 20,000 feet. They could be both. They could be water droplets or ice crystals, usually depending on the time of year and the uh, uh, latitudes that they're at. Um, and again, altostratus and altocumulus are the prime examples. Low clouds are anything typically below 6,500 feet. Um, it says mostly composed of water droplets, and that is typically true. But of course, in the middle of winter, you can certainly get a lot of ice clouds even down in uh, much lower altitudes. And again, if because it can contain ice particles and snow if the temperatures are cold enough. Here's a good chart. If you want to go to this website, I did check it and it's still good. You get this nifty little cloud uh, chart that NOAA and NASA put together some years ago, and it just shows all the different types and some of the examples of those. So let's play a little game again. Let's name this cloud. Is this just based on this picture? And I know trying to judge things from a picture on the internet is not always great. But does this look like a high, mid-level, low, or a vertically developing cloud? Any guesses? All right, I'm not seeing any, but oh, okay. A few people said high cloud. And that is correct. That is basically cirrus clouds. When they kind of look like horse tails, then that's typically a high cirrus cloud. How about this one? Is this a high, mid-level, or low cloud? I won't go into the vertically developing cloud. Any ideas? Guesses? Mid-level cloud? And actually, it's a low cloud. It's cumulus. That's a cumulus cloud, typically around 3,000. Uh, 10, it says 3 to 10,000 feet, but typically that's a the base of the clouds are around 3,000 feet, and that's what we consider. But they can grow up to about 10,000 feet. But this is technically a low cloud. Um, how about this one? Mid cloud vertically developing. Yep, this is actually a thunderstorm. It's a cumulonimbus cloud. Uh, we don't see a lot of these kind of well-formed clouds around here, just because a lot of times other cloud cover gets in the way, but especially out in the plains and that area, you see these really well-formed thunderstorms. They basically explode up, and then they hit the troposphere, and then they spread out, and you get this nice round shape if there's very little wind up in the upper atmospheres. And you get these. This actually looks like a supercell, so it's probably the whole thing is rotating. So, all right. So as I mentioned a little while ago about high and low pressure, high pressure systems form when air cools and sinks. So a lot of times you'll get high pressure that comes out of Canada and moves down because that air is already typically colder than at least here in the lower 48. So cool air is denser than warm air. So as it sinks, so it does sink as it gets closer to the Earth's surface. Um, the sinking air creates a column that increases the pressure at that location, so it's pushing down on the Earth. And you'll typically see that as the big blue H on a weather map. So the pressure's pushing down, and the winds have no choice but to go out. And you can see this kind of here on the right side of the diagram. The winds go down, and then they're pushed out because it's now low pressure systems form when the air warms and rises. So as the air rises up, it cools, and as it uh, as it cools, that water vapor in the air condenses to form clouds and potentially precipitation, typically shown as the L on the weather map. And you see here as that air rises, well, something has to take its place, so the air from the surface moves into a low pressure area and again away from the high pressure area, so they're trying to get back into equilibrium and and everything out. um, Julie said like a microburst, and yes, that's actually a uh, uh, for the high the high pressure, not quite like a microburst because the winds are much slower. But we will talk about that in the thunderstorm area here in a few minutes. How does air pressure impact those with seasonal allergies? Um, I'm not an expert on that, but I can tell you that yes, the high pressure especially does affect your sinuses because that's higher pressure pushing down on you and does tend to cause some sinus problems. As far as allergies, um, that's more of a dust and pollen and issues, and weather affects those. Whether it's high or low pressure, it's probably more of a wind issue, and both high and low pressure can give you strong winds. So um, that's a good question, but it's probably not a question I can really reliably answer uh, from a from especially from a medical standpoint. Okay, there we go. So at the surface in the northern hemisphere, winds flow counterclockwise around the low pressure area. So they're moving cyclonically is what we call it. And then they move clockwise around the high pressure. And you can see in these two diagrams on the right, high pressure here, the winds are moving cyclonically. So, uh, and here at the surface, you got this big low pressure system over North Carolina. And so the winds are generally, if you're in the Midwest, should be coming from the northeast to the northwest direction. So that. So, and again, they're trying to flow from this high pressure system down to this low pressure system to, uh, try to fill it in. Um, the lines of equal pressure between these highs and lows are called isobars. So you may hear that on your local TV broadcast, talking a little bit about that. And so you can see them here. So these are just lines of equal pressure. Um, and surface winds generally flow at an angle to these isobars from the high to the low pressure. So they're not going to necessarily flow like this arrow shows right down through them. They're actually going to be flowing somewhat, in this area, probably from almost a due north direction, and then down and around. So uh, the we have this thing called streamlines that we use in meteorology that actually depict this much better than the charts that we typically show on TV. Um, and I kind of wish that we would go to that for that, but I think it would probably confuse a lot of people. So here's a surface analysis and pressure chart that you might see on the internet or on TV occasionally. This one is a little bit busy, but you can let me get my, I don't know if you can see my cursor, but here's a low pressure area right around Lake Erie, and then there's a cold front that's coming through the Tennessee Valley. You got a high pressure area over Missouri, and then you got another low up in right around the Canadian border in North Dakota, with a little bit of a warm front and then a cold front behind it. And so it gets a little bit busy. You can see the isobars here, and then these little lines here, like the one going through South Dakota and Nebraska, uh, typically define or refer to a trough, is what we call it. So it's not really a front, it's not really, but it has some kind of uh, weather phenomena associated with it typically. And here's just another example, and this one I like a little bit better because it's a little bit cleaner as far as the fronts are depicted. This just shows a few of the weather observations in that. So weather fronts, excuse me, we're going to talk about each one. A surface low pressure system usually has some kinds of front or fronts associated with them. And that front is a boundary between two different air masses. So it may be a big temperature difference. It could be a wind shift, or it could even be just a difference in moisture content within that air mass. But that's how we typically define a front. There's four types of fronts that you've probably seen: a cold front, a warm front, a stationary front, and an occluded front. And so a cold front is depicted by the little blue triangles on a line. Um, Normally, the air in front of a cold front is warmer than the air behind it, i.e., that's why they call it a cold front. Um, with a cold front, the cold air advances and displaces the warm air because, again, we mentioned how it's more dense and heavier than warm air. And you can see here on this video, here's the warm air basically going you know, north to or south to north. Here comes the cold front, pushes that warm air out of the way and pushes it up. That condenses the clouds. Clouds form and rise, creates this precipitation. And if you split, and then the winds behind it are typically, now they're coming from the north heading south as opposed to the other direction. And, play this one more time. And if you look down here at these weather observations here, and you see, temperatures, mid 70s, dew points in the middle 60s, so it's very warm and humid. And then behind it, your temperatures can easily drop, 20 to 30 degrees or more. You get a little bit of rain, the dew points plummet because of the cooler, drier air that's in behind these. Um, a warm front is with a warm front, the cool and cold air ahead of the front is displaced by the warmer air that's moving in. So it's the opposite of a cold front, obviously. But with the warm front, the cool air ahead of it has to retreat before the warm air can advance because that cold air is denser and thus heavier. It doesn't want to move. So to some extent, the cold air has to decide to move out of the way before a warm front can move in. Um, and here's another example of that. And as the warm front slowly advances, and typically it moves a little bit slower than a cold front. As it starts to advance, the warm air actually is pushed up over the cold air and forms these clouds. So you get more of a stratiform cloud, and that's why you can get warm air above the surface, but you still have cold air at the surface. You can still get farther out ahead of it, you might get snow, but you can get sleet, freezing rain, and even rain. So this is typically the setup for when we get a freezing rain or a winter weather event. Where there are warm fronts in winter and cold fronts in the summer. It's actually both. We get warm fronts in the winter, and we get cold fronts in the winter. And in the summertime, it's typically more of a cold front. You see, warm fronts are fairly rare in the summer, actually, because the air is already warm. Springtime is when you see, in winter is when you see a lot of warm fronts. We actually saw the one we had the other day with the freezing rain was actually a warm front that pushed through before the cold front came and pushed everything out and cleared us up. Um, Warm fronts typically don't last as long as a cold front. A warm front may come through and only give you a few hours of warmer weather before that cold front comes through and pushes everything away. Um, Thunderstorms can form in the summer along a warm front. You actually can get some very severe weather associated with the warm front because of that, as that warm air pushes up over the cold air and it starts to mix in. So uh, you can, like I said, you can get a little bit of both. All right, finish that up. Come on. There we go. Now, a stationary front occurs when two air masses, warm and cold, meet, but they can't move each other out. And so you get these are especially prevalent in the springtime. Um, uh, Usually April, early May timeframe is when you'll see these. You'll get these fronts that come through and then they just sit there. And you'll see, to the north, and this is not a really good one because the temperatures aren't too different. But a lot of times in the north, you'll see temperatures in the 50s and 60s, and down in the south, you'll see 70s and maybe some 80s. There'll be a good 10 or 15 degree difference in them. And a lot of times that warm air will run over the stationary front, so you tend to get a lot of precipitation just to the west or just to the north of the cold front. Let me try that again. You get a lot of precipitation just to the north of the stationary front, and those things can sit there for days. And because they're neither one is strong enough to move the other one out. In a lot of cases, they don't actually move out. It's just that um, the mixing around them eventually just washes it out, and things return to normal. You really don't see anything pushing it out unless another cold front comes in and pushes it all out. You also may see it, and you see it in this example here. Uh, in say the maybe the Williamsburg area down into the North Carolina Outbanks where it's showing this. Um, I suspect in this case this is not a stationary front at all. This is probably due because this was September. Um, has something to do with more of the air mass over the ocean versus the air mass over land. Um, and there just being a difference because the ocean temperatures versus the land temperatures. So that can technically create a pseudo stationary front. But I always disliked doing that because that's not truly what a warm or what a stationary front is, but the conditions for that are the same. The last one is an occluded front, and that's a composite of two fronts that basically the cold front overtakes the warm front, and then it just kind of combines into one. You get this almost stationary front. Um, with the then as it gets down to the south, you see the oops the typically a cold front. Now in this case is showing kind of as two stationary fronts, but really this one to the left or to the right is probably a warm front. This one is a cold front. But it's just become disassociated with the low pressure system itself. And you can get a cold occlusion and a warm occlusion depending on where the cold air versus the warm area is on those. Uh, Precipitation is, if it's rain, it's liquid precipitation that reaches the surface in the form of drops that are greater than half a millimeter in diameter. Um, Basically, they just sit and aggregate up in the air until they become too heavy to be sustained by the wind and the air rising, and then they start to fall. Snow is a precipitation or in the form of ice crystals formed directly from the freezing of the water vapor in the air. Sleet is a little bit different. Sleet is rain that then freezes and turns to ice pellets before reaching the ground. So it the temperature on at the surface may or may not be above freezing, but there's a layer of air above the surface that's below the freezing that is underneath an air layer of air above freezing. So as that raindrop falls through, it hits that freezing air, it freezes into a little ball, and that's where you get the sleet from. Um, as opposed to freezing rain, which may have started out as snow, hits that warm layer, and then melts and becomes rain again, and it may encounter this freezing uh, temperatures near the surface of the at the ground, but it doesn't have time to freeze, and thus it hits the ground and then freezes on the ground. Um, so what happens to cause a blizzard? So a blizzard is the only difference between a regular snowstorm and a blizzard is the wind. If the wind is greater than sustained wind is greater than 35 miles an hour for several hours, that is the definition of a blizzard. So it may not uh, and it could last for a few hours or it could last a couple of days, but it all depends on the wind speed. That's what determines whether it's a blizzard or just a regular snowstorm. You can get 2 feet of snow in 10 mile an hour winds. That's not a blizzard. You can get 1 inch of snow and 40-mile-an-hour winds for 3 hours. That is technically considered a blizzard. So it's like I said, it's all depends on that, and it's all about that low pressure forming and really spinning up and becoming strong and increasing those wind speeds. Um, Hail is basically lumps of ice, always produced by convective clouds. It has to be a diameter of 5 millimeters or more, which is basically the size of a little pea. Um, while smaller pieces, particles similar origin may be classified as ice pellets. But hail is as a convective cloud rises, that air condenses and cools and freezes, those ice particles start to basically hit each other and start to form, or they're in super cold water. That water collects on the ice, and that hailstone keeps getting bigger and bigger, and it either becomes so big that it's um, that the air can't sustain it and it starts to fall back, or it's pushed out of that rising air into in either non-rising air or air that's falling and starts to head towards the ground. It may not reach in a lot of cases, hail never reaches the ground as hail because it melts before it ever hits the ground. Graupel is similar to that. It's call it soft hail or snow pellets, but it's precipitation that forms when that super cooled water drops, and that's just water that's hasn't frozen, but the temperature is below freezing. Um, it's collected and freezes on falling snowflakes and forms these little balls of we call it says opaque rime, but basically little balls of ice. Um, And surprisingly, that happens once or twice a year in our area. A lot of times in March or April, so we'll get these little graupel storms that happen. And the weird thing is the temperature is typically 40, maybe even 50 degrees or more when that happens, and it's sometimes enough to almost cover the ground. This is a great chart that kind of shows the what you would get depending on the air temperature. So when you get all warm air from the surface all the way up, you're going to get rain. Um, a lot of clouds, no matter even in the hottest part of summer. A lot of times, if you fly through that cloud, you're still going to see snow or ice in that cloud. It's still going to be below freezing. So almost all precipitation starts out as snow. But you get this big warm air, it melts, you get rain. If you get a big warm layer, but then you have freezing temperatures at the surface, that's when you get freezing rain. When that freezing layer is high enough up or deep enough that the rain can refreeze, that's when you get sleet. And then when there's no warm layer at all and it's all below freezing, that's when you get snow, and that's actually what we're going to see in our area tonight, but I don't think it's going to reach up to your area, at least for this storm we're getting tonight. For thunderstorms, a thunderstorm is considered severe if it produces hail at least 1 inch in diameter or wind gusts of at least 58 miles per hour. So technically, if it doesn't have one or the other of those or a tornado, it's not considered severe. Doesn't mean that it's strong, doesn't mean that it's not deadly, or can cause damage. It's just that's the definition of a severe thunderstorm. Um, and it doesn't matter, a thunderstorm can, give you 4 inches of precipitation. That doesn't mean it's severe. But obviously, you get a lot of heavy rain from these thunderstorms, can cause flash flooding. Every thunderstorm produces lightning. That's kind of the definition of a thunderstorm, which does kill more people in some years than tornadoes and hurricanes. Um, but in the U.S., that number has declined significantly over the past 20 to 30 years, mostly because of publicity and people being told, when thunder roars, go indoors, things like that. Thunderstorm deaths really declined in the U.S. They have not declined that much in especially developing countries, um, especially places in Africa. They see at times hundreds of deaths a year due to lightning. I do have an asterisk beside that. It says the numbers continue to decline in the U.S. That is not true for this year. The last few years, the number of deaths in the U.S. has been around 10 to 13. This year it was 20. Um, probably just a statistical anomaly that it happened. And I know in some cases there were, I think, 2 or 3 cases this year where multiple people were killed by lightning. So that probably pushed the death toll up a little bit higher than it has been. But hopefully that's not a trend, and like I said, it's just an anomaly. Um, High winds cause the damage to homes and blows down trees and utility poles and can create widespread power outages. Um, a lot of times people are every year killed or seriously injured because they either didn't hear the warnings or they just ignored them. Um, and that's the one thing that the Weather Service is really pushing and studying. They now employ social scientists to figure out how they can get the warnings out and get them to the people, and for the people to actually not only understand them but heed the warnings and do something to take care of themselves. So here's a few safety tips. Watch for signs of a storm, darkening skies, lightning flashes, increasing winds. Any of those, especially in the summertime, can be a precursor to a thunderstorm. Listen to your local news or your weather radio for emergency updates. I know a lot of times you can even get them on your phone now. Um, Really, no place outside is safe when there's thunderstorms in the area. So you do need to try to get indoors. If you do hear the thunder, that means the lightning is close enough that it can strike you, and that does happen. Uh, Immediately move to a safe shelter, some kind of building with electricity or plumbing, or an enclosed metal top vehicle with the windows up, as we talked about earlier. Um, but sometimes you're going to be outside, if you're hiking on a trail or something, and you can't reach a safe building, at least avoid high ground. Um, get away from water, get away from tall isolated trees. Um, if you are hiking in the woods, yes, probably is best to take cover around trees. Just try not to make sure you're not around the tallest tree around to minimize your exposure. And certainly stay away from things like uh, metal fences or bleachers and things like that, because those are just lightning rods, basically. Picnic shelters, dugouts, sheds, and things like that are not safe places to be. So if you're having a picnic in one of those shelters out at the park, the best thing to do is really head to your car and try to get out of there, and don't stay under that shelter. Um, and then stay there for at least 15 minutes or so after you hear that last sound of thunder, just to make sure that you're being safe. If you're indoors, stay off corded phones, which most people don't have anymore. But if you do, don't stay on those, or computers or other electrical equipment that put you into contact with electricity. Um, so basically, don't touch anything that's plugged in. Avoid plumbing, including sinks, baths, and faucets. I know I've talked to a lot of people, and they're like, "Oh yeah, well, it was a thunderstorm, so I went and got my shower." Um, that's probably not a good thing to do, because if lightning hits your house, water is a good conductor of electricity. It will run through your pipes and could potentially at least shock you, if not do worse. So avoid doing things like taking a shower during a thunderstorm. Uh, the Stay away from windows and doors. Stay off your porch, as lightning could um, can actually go through windows and things. So just avoid those. Don't lay on concrete floors. Don't lean against concrete walls, because concrete is a conductor of electricity. Um, as a last resort, here's some other tips. If you're caught outside with no shelter anywhere, these actions can reduce your risk. Again, immediately get off elevated areas such as hills, mountain ridges, or peaks. Um, Put down a golf club. You're you're just holding a lightning rod. Don't do that. Put it down. Uh, do not lie flat on the ground. with the exception of if there's a tornado coming, then yes, get flat on the ground. That's uh, the kind of the least uh, or most best option, I guess. Um, don't shelter again under an isolated tree. Don't use a cliff or a rocky overhang for shelter. And then get away from ponds, lakes, and any other body of water, and stay away from those objects like barbed wire fences, power lines, windmills, things like that that conduct electricity and that can strike many miles from home. Um, let me see. And I see we're way over time, but and I understand if people need to leave, but I got about probably 10 more minutes or so of things to go through. Tornadoes. I know everybody is fascinated by tornadoes. Um, this question: I have a concrete house with concrete floors and walls. Am I cooked? No. And the reason you shouldn't be is you should have your house grounded. Um, if you go outside, and especially if usually it's near where if you have a gas line or electric or something coming into your house, there should be um, a line coming out of that is hooked into the ground, and that grounding wire should keep your house safe. So that if it does hit, the electricity should run down that wire into the ground and not through your house. So that's why you always make sure that your house is grounded properly. So, uh, thunderstorms can occur any time of day or night, any time of year. Obviously, they don't typically happen in the winter, but they can, and they have. Late afternoon through early evening in the spring and early summers when most of them happen in our area. Um, Unlike the plains, most of the tornadoes that occur in especially the whole mid-Atlantic and Maryland included are rain wrapped. They're very difficult to see. Um, they're not like the pretty tornadoes that you see in the plains that you can see from 20 miles away. Um, you won't see them until they're on top of you, just because the one trees in the way, but also the like I said, they're rain wrapped. Um, if you are under a warning, go immediately. The best was go underground to a basement or storm cellar. If you can't, then go to an interior room such as a closet, hallway, or bathroom. If you are outside and you can't get inside, lie in some kind of ditch or get as low as you possibly can. Obviously, be aware that if you're in a ditch, that ditch could, very quickly flood. Again, just be aware of your surroundings and do the best you can. And take those warnings seriously. Yes, there's a lot of times false alarms for tornadoes and other things, but you know don't be a statistic because the one time you think, oh, this isn't for me, will probably be the time it is. So just take those warnings seriously. Um, and it's just my favorite quote because I'm a WKRP and Cincinnati fan. Uh, a little bit about tropical weather. You hear about storm surge, and that's the rise of water generated by the storm's wind hitting the coast. So a storm surge can reach heights up to 20 feet or so and can span hundreds of miles of coastline. And that's all about that wind from that storm pushing that water up against the coastline, creating those waves that are much bigger than normal. But it can also push that water, hundreds of meters and even farther inland. So that's why those areas right around, right immediately along the coast, um, are usually devastated by a direct hit. Is the storm surge? It's not the wind that causes that damage. The storm tide is basically the same thing as it's a combination of the storm surge and then the astronomical tide. So a storm that hits during high tide will typically be much worse than a storm that hits at low tide as far as storm surge. Um, and then heavy rainfall and inland flooding. Uh, we think about tropical systems and hurricanes. Yeah, once they hit the coast or once they move off the coast, oh yeah, we don't have to worry about it too much. But a lot of times those storms produce widespread torrential rains, even well away from the coast of 6 inches or more. We've seen a couple of examples of that in the last few years of that 50 plus inches in Texas from Hurricane Harvey, and then 20 inches plus there in the Asheville area last September, I think it was, with Hurricane Helene, that results in deadly and destructive floods. And so just because the hurricane has moved inland, things don't always go back to normal, and it can be really bad. And actually, flooding is the major threat from tropical cyclones from people living inland. It's tornadoes are second, but flooding usually is the biggest issue. Um, High winds, even storm force winds are strong enough to be dangerous, but hurricane force winds of 74 miles per hour or more can destroy buildings and mobile homes. Even tropical storm force winds 50 to 60 miles an hour, if they are sustained long enough, can do that as well. And I mentioned that hurricanes and tropical storms can produce tornadoes. They most often occur in the rain bands well away from the center of the hurricane, almost always in the north east portion of that area. Um, and I actually saw a good uh, study on this several weeks ago, looking at some of the, especially for the East Coast Atlantic, from the last 5 years or so of the tropical storms or hurricanes that have moved up uh, along the coast or have hit Florida and then moved up through the Carolinas and Virginia and Maryland. And they track the hurricane or the tornadoes that occurred from those hurricanes, and almost every single one of them was to the east of the track and typically just a little bit to the north of where the low was at the time. Um, so it's something I think we always kind of knew, but we always assumed that it was also possible on the northwest side of the hurricane and this tropical storm, and it looks like that's almost never the case. So it's pretty interesting. Typically around here, if you get a tropical storm come through, there's really no need to evacuate unless you live in a low-lying area prone to flooding. But again, be prepared for that flooding, some wind damage, and especially power outages. Here's the hurricane intensities, the 1 through 5 that we all hear about. The sustained winds, typically it rises out to 15 to 20 miles an hour to go to each different stage. Um, really anything, Cat 3 or more, will create really devastating damage with that. Now, typically the winds, those kind of winds are really close to the center of the eye of the hurricane. But you can get gusts occasionally that go out quite a bit farther from that get up to those speeds. My thoughts on creating a Cat 6 level. Funny, the American Meteorological Society actually, on their community board, that was a topic of discussion a couple of weeks ago, on whether we should create a Cat 6. And um, I'm under the opinion, no, there's no reason to. If Cat 5 is catastrophic damage and basically anything in its path is going to be destroyed, Category 6 not going to add anything to that. And in fact, I think if you said, hey, this is a category 6 storm, and then it dives down a little bit to category 5, people are going to go, oh, so it's not as bad as it could have been, and they're going to let their guard down. So I think what we have now is fine. Um, Now, we may have to, if we start seeing that storms, are frequently higher, than, 160 miles an hour or so, maybe we can take a look at it, but I just don't think it would do any good at this point. And it's something that's very rare to begin with. And there are there is still a lot of discussion within the meteorological community on whether climate change will impact the intensity or number of hurricanes, and it kind
Good
of
boy,
goes
buddy.
back and forth. Um, so we'll just have to see. What about creating something to warn about storm surge potential? That is in the works.
Good boy,
Uh,
boss.
yeah,
Good boy. Come on in.
yeah. Um, so yeah, the storm surge potential, that is something that's being discussed, and I suspect that they're already doing storm surge warnings. I think that they're going to continue to tweak that as they as that becomes more rooted in current forecasts and things like that. Um, it's something. Storm surge has always been very difficult to forecast, but I think we've gotten a lot better at it in the last few years. And now that we have, I think we can certainly do something like that. Uh, Common weather alerts you're probably all familiar with, but do you really know what they are? And these are the three. A watch is issued when the risk is there, um, but it hasn't happened yet. So, it's possible, and we think it's going to occur, but there's still some uncertainty. So it's basically provides you enough lead time so that you can start to plan on it. So you could have a tornado watch or a severe thunderstorm watch or a hurricane watch, things like that. It's just, you know, conditions are favorable, but it has not occurred, and it possibly might not occur, but we think it's going to. A warning is it is occurring, or it's about to occur, or we know that it's going to happen with good certainty in the near future. So it's only for conditions that pose a threat to life or property. Again, severe thunderstorm warning, tornado warning, hurricane warning, tropical storm warning. It's something that, hey, you take this seriously. It's about to happen. Uh, Protect yourself and protect your property if possible. An advisory is for something it's kind of a warning. Yes, we think this is going to happen, but it's more about this is going to cause an inconvenience. Um, but if you don't take cautions, yes, it could still threaten life or property. They were going to go away from advisories and go to these weather statements. I think they've backed off on that. A few years ago, that was almost a given that they were doing that. I think they backed off of that because they did not get rid of the advisories, and they're still doing them now. In fact, we're under a winter weather advisory here tonight for the snow, um, and I thought I changed that out, but I guess I didn't. So, um, because I didn't, I fixed it here. So, um, for winter weather, you have a winter storm watch, again, favorable, but doesn't mean it's going to occur. Winter storm warning, but that only is for snowfall of 4.5 inches or more. And sleet is also counted as snow in that. So anything below that is typically an advisory, um, but for snow. Uh, Anything above 1/4 inch of freezing rain is a winter storm warning because freezing rain is basically ice, and ice is a big problem because of power outages and travel issues and things like that. A winter weather advisory is snow between 1.5 inches and 4 inches and any measurable amount of freezing rain. So again, it's just, hey, this is, we might get a small amount of freezing rain, still going to be a problem on roads, um, but it's not going to be that terrible. There is one exception for this area. For the DC area, they do have a separate winter weather advisory um, for up to 1 inch of snow. And that is especially for the morning and evening commute periods. Um, they were going to talk about making that, and it still might become a special weather statement. But as of now, it is still a winter weather advisory, and I believe they have issued that for DC, the DC area tonight and tomorrow morning, because it does look like that at least that area we'll see a little bit of snow overnight into tomorrow morning during the commute. Um, some weather forecasting basics. Basically, we just take the physics and current technologies and science, and we're going to predict the state of the atmosphere later on, whether it's a few minutes or days or weeks out. We use numerical weather prediction models to basically create these simulations of the atmosphere, and we take the analysis of the weather observations as that starting point and evolve the atmosphere forward in time using physics and fluid dynamics. Here's a weather forecast. Looks a lot like the analysis. It's just for future time. We can do it for temperatures, just showing what we believe the temperatures will be at a future time. We can do it for forecast or for precipitation to show what we think the amount of precipitation is going to be at 24 hours or 48 hours or something like that. I will say, if you see anything that goes beyond a week, don't believe it. We're getting better, and even out to 10 days, even 12 days out, there's usually a signal there. So, you might think, yeah, 12 days out, it says it's going to rain. It probably is, but it's maybe a day before or a day after that or so. But typically, we're pretty good about forecasting an event in a general time. But we would certainly not say, you're going to get a 1/4 inch of rain 12 days out, because the science just isn't there yet. Here's some good satellite imagery showing, some of the things that we use to help forecast with. I can watch these things all day just because I love watching the formation of the clouds and things. We can do it with weather radar, showing where precipitation is occurring. But here's a video that I suspect that you'll all recognize, and this is from the derecho that came through in June of 2012. This is just the radar imagery that's spliced together along with lightning, and the little white lines are basically all the lightning flashes that were occurring as this derecho moved through the DC area. Red is stronger precipitation and wind, and the severe part of the storm coming through, and it's just cool to watch that as it blew through the area. The little dot there in the middle is actually the radar there at Dulles at the Sterling National Weather Service office. That gives you kind of an idea of exactly where everything is at. So with that, we already talked about these. Here's just some miscellaneous things that for everybody. And again, we'll get you these slides. Just some things to remember. Thunder roars, go indoors. Don't drown, turn around. the Celsius to Fahrenheit conversion, millimeters to inches, things like that. The snow precipitation ratio is typically about 10 to 1. So for every inch of liquid precip, you get about 10 inches of snow. In colder temperatures, especially mid 20s and below, that ratio increases. The snow basically gets a little drier and fluffier. So you can get up to about 15, excuse me, 15 to 1, even 20 to 1. Um, Sometimes when the temperature is 32, 33, 34 degrees, that ratio goes down to about 6 or 8 to 1. Um, and then here's some good weather sites if you're websites if you're interested, and all of these are still good. I just checked them the other day. Um, for the National Weather Service office, Weather Channel, AccuWeather, some models, and then Capital Weather Gang at the Washington Post. Um, they're actually very good about explaining, different phenomena and weather occurrences and things like that. So, um, with that, um, just let you know, part two of this, the climate part, will be on 5 March of 2026. Those are the topics that I'll be discussing. And this one, actually, the climate part will probably be a little more focused on Maryland and the surrounding area than the weather one is. That was kind of more general. But that's it. So, any last questions? I see some thank yous. I don't see any. Uh, and you're right. The categories for uh, the watches and warnings, they certainly do create some confusion. And we're trying to work on that again to see, is there any way to make that a little bit better. So, all right. Well, with that, I think we're good, and I will turn this back over.
Okay.
There you go.
Thank you so much. As Randy, I think this was a great and it has a presentation with an awful lot of information, and it's a
Yep.
big, large, complicated topic. And it was really
Very so.
great to see all that. And you did warn me you would probably take a little extra time, and
Yeah,
I think
sorry
that
about
was
that.
fine.
That was even longer than I thought. So,
Well, I think it worked out well. As Randy said, he has agreed to present a second webinar on Thursday, March 5th, 2026. It will be at 7 p.m. again, and it's entitled Part 2, Climate Patterns and Change, Understanding the Long View. The registration is already open on Nature Council's website under the drop down for events. And again, that's naturecouncilfc.org. Um, and as I noted earlier, the recording of this webinar will be posted to the Nature Council website within a couple weeks. Randy has said he'll send his PowerPoint over, and that would also go on our website. And so I want to thank everybody for joining us and wish you all a very good night.
hey, Patty, real quick.
Sure.
The when I send the slides, I will not be able to send the deratio video. It is just so big, it'll clog your system. So I'll delete that out to send you the rest. Um, I can promise part two won't be as long as part one. But finally, here's my contact information. If you have any questions, please, feel free to contact me, and I'll be happy to answer any questions you have.
Okay. So thank you, and thanks everybody for joining us tonight. And that will end our session. Okay. Okay, I'm going to end the session now.